Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today it's actually not one theorem, but like a more an idea type of theorem if you want. So what is a coherent theorem? That's the topic for today. So a coherent theorem, not the coherent theorem or something like that. No, it's just really a collection of different theorems, and they kind of have all the same underlying idea. And it's this idea that, well, you shouldn't underestimate something like associativity. Associativity is a little bit subtle, as we're going to see, and there are kind of a little bit of beautiful ideas involved, how to geometrically interpret associativity, and then it kind of becomes more clear why we should, well, why we should expect associativity to hold in most natural setups. So let's actually just get started and have a look at associativity itself. So the geometric interpretation of associativity is not quite clear. I'm going to run a Mathematica demonstration in a second to, well, convince you, hopefully, that really it's not so obvious. Associativity is not so obvious as you think. So our brain tends to trick us because, well, associativity is something we usually take for granted. So let's have a look again. So associativity is just this condition, say, for multiplication. Um, as I'm as I said, I'm just will explain that picture in a second. But associativity can hold for multiplication or for addition or some other form of operation. And usually, as I said, so kind of our brain kind of assumes that that's true anyway. So of course it's true. It's associativity. It's kind of one of those little technical glitches that it's true, right? It couldn't be false. But actually, that's tricky, right? It's very tricky because it's not trivial. For example, if you just change the operation, for example, division is not associative. And a lot of people, including myself, do this mistake that kind of you kind of ignore that division is not associative, and well, you get wrong results. So in my little example here, you could check whether I have messed up the calculation. It's very likely that I've messed up the calculation anyway, but whatever. So 4 divided by 2 divided by 2. There are kind of two ways to bracket this expression, and you will get two different results. So really, associativity is not really as trivial as our brain tricks us to think it is. So let's have a look at the demonstration, which kind of shows a little bit that associativity for addition is reasonably obvious, while associativity for multiplication isn't maybe not as obvious as you think it is. So here's a Mathematica demonstration. The link is, of course, in the description. And well, it's a demonstration of associativity, as I said, for addition or multiplication. So I can change to multiplication in a second. So for addition, it's really just a very, very easy idea that you have three piles, a green one, a blue one, and a red one, right? Green, blue, red. And there's some numbers associated with it. So in this example, the green is 3, the blue is 4, and the red is size 2. And well, on the other side, it's the same. And the rebracketing here, so 3 plus 4 in brackets plus 2, 3 plus in brackets 4 plus 2 is just obtained by cutting those piles. Well, we have three of them, on a line, and you cut them at a different position, right? So 3 plus 4, you first well, add those two together, which is just shifting them next to one another, and then you would shift the two next to it, or do it the other way. So this is kind of clear, and you can vary the numbers. And as you can see, if you vary the first number, well, it's a very local property, right? So yeah, this is kind of obvious that this should hold, right? It's kind of a very kind of obvious property. With contrast, in multiplication, it's not so clear to me at least. So this picture works as follows. Here you have 3 times 4 times 2. So 3 times 4 is the square in the front, of course, 3 times 4, and you have two of them, so you just align them next to one another. If you do it the opposite, right, 4 times 2 is a little square here, and you have three of them. And this actually is the same. And I don't know how you feel, that doesn't seem to be super obvious to me why this is the same. And indeed, if you vary the numbers a little bit, um, I mean, those brick brick collection, whatever you want to call them, they're the same, right? So this associativity says that those brick collections are the same. This is not so obvious, I think, in contrast to addition, which was kind of pretty clear in some sense. Multiplication seems to be much more subtle. So why should those give the same result? That's not obvious to me. So associativity always comes with a little catch. So you need to be careful, right? Our brain likes to trick us. It definitely likes to trick me a lot. So I personally, I get this wrong here with the division all the time. I get it wrong all the time. I can't divide. I would ask a machine to do it. I hopefully ask a machine to do this calculation that you see here right now, because otherwise it's probably wrong. Anyway, so that's not what I'm going to address actually in this video. I just want to warn you that there's more about associativity than you think. There's another aspect of associativity which is far from being obvious, and actually the topic of this video. It's this observation that, okay, associativity usually is written in this expression here. So 3 terms and 2 brackets, so 2 bracketings or whatever. But there are various versions here, like this one here, right? So main question, the even worse question if you want, why on earth does the small equation here, just involving 3 terms and 2 ways of bracketing those 3 terms, why does it imply something much more fancy like this one? And it's not really much more fancy, it's only 4 terms. You can imagine now 512 terms, and God knows what kind of ways to bracket them. So why should that be true, actually? That's really not obvious at all, right? Already for this 3-term one here, I said you need to be careful with the division, for example. And now I'm asking something really fancy. And this picture seems to completely fall apart, in my opinion. At least I can't see how this should work. So here is just the easy expression. It's already not so clear in this geometric picture. And now I have, well, 512 different expressions, and God knows how many ways to bracket them. And this gives some very strange brick configurations, and they all should be the same. That doesn't sound really obvious to me. But there's a really beautiful way of proving this, and I'm going to explain that, and that's the example, or example basically, of a coherent theorem. So let's have a look. So here's a picture of associativity which I really like. It's a question, what is the wrong definition, what is the correct definition? So in some sense, the wrong definition is what you see upstairs, and the correct definition is what you see downstairs. Whatever, wrong and correct are, of course, in huge quotation marks, because there is no wrong definition. A definition can't be wrong, right? It's a definition. It just can't be wrong. It can do the wrong thing, but it can't be wrong itself. Anyway, so A, which is the upstairs one here, this is A, and B, which is the downstairs one, the one at the bottom, B, are the following kind of 2 different ways to define associativity. The simple one that you usually see everywhere, or actually the correct one in some sense, kind of you get the same result regardless of the brackets, right? So no matter how you put brackets, you really get the same result. It's kind of the correct statement of associativity, because you don't want to worry about brackets. That's the whole point about associativity. So why should I just check this little equation here if I actually would need to check huge bracketings of huge expressions? So kind of B is the correct one, and A is kind of a little bit of a shaky definition if you want. I'm not quite sure what to do with it at first glance, right? So why should that be enough? Now you would wonder, wait, in every textbook I ever read about anything, about groups or whatever, you usually find this as a definition of associativity. So what's wrong here? What's wrong with the slide? Well, there's certainly a lot of things wrong with my video, but so actually here's nothing really wrong. It's just a different viewpoint on the definition. So what I would like to explain in a second is that they're equivalent, right? The philosophically correct way of defining it or of doing it would be to use B as a definition and show that A implies B, and obviously B implies A. So if I my assumption is that any bracketing is the same, then of course the small one is the same anyway. So B definitely implies A. The big meat here, or the real meat here, is that A implies B. So right, I say it again. So kind of the philosophically correct definition of associativity would be, well, B is the definition and A implies B, right? That's kind of the point. And then you don't need to worry anymore. And you have a pretty cool result, actually, because a finite number, a very finite number of conditions, namely 1, implies, well, an infinite number of conditions, which is kind of the blueprint example of, it's actually the definition, if you want, of a coherent theorem. So that's kind of a blueprint example of a coherent theorem. Let's have a look at my pictures, actually. What do they mean? So I would like to think of associativity in the following way. I have 3 symbols or more symbols. I won't write those symbols anymore. And well, whenever I multiply them or whatever kind of my operation is, I kind of merge them together, right? GF and then GF. I omit the product here because I kind of think about it could be an addition or could be any other type of operation actually here. So I have GF and then I merge H to it, and it looks like this thing here. So you first merge the right to expression and then the left to everything, or you can do it the other way around, and it would look like this. And associativity is saying that those two graphs are the same. That's kind of the statement of associativity. The wrong the wrong definition of associativity says that those two graphs, little graphs, locally are the same. And the correct definition says, well, any kind of different ways of doing that, there's zillions of them. I just illustrated two. All of them are the same. So you have a huge bunch of graphs that should be the same instead of having two graphs to be the same. Right? That's a huge difference. It's really huge difference. So B involves infinitely many graphs that should be the same, and A just involves two, which is two is certainly smaller than infinity. I think so, at least. And let's have a look at the proof. The proof is pretty cute, actually. So the proof is given by looking at a certain type of space. I call it K4 in this case. So 4 is just the number of endpoints. 1, 2, 3, 4. So I always have 4 here. And I call it K4. In general, of course, Kn, with n number of endpoints. And you want to prove that, remember, that the easy form of associativity implies the general form of associativity. So the small one implies a big one, if you want. And the statement is as follows. You list all those graphs. So for 4 expressions, there are 5 ways of putting brackets. So let me just, in order to be completely clear, this one would be, so FG, and then H, what is the next one? I. And the bracketing here would be, as you can see, those two, it would be this bracketing. Right? So this one should be, for example, this one here, where I put the bracket first in the middle, then I put my bracket here, and then I put my bracket here. Right? So it's kind of different ways of bracketing expressions. And as I said, for 4 symbols, there are 5 ways, and these are those 5 graphs. This is actually pretty nice. So again, input is at the bottom, output is at the top. And you just read along from bottom to top, and that's your expression here. And the statement is that all of them are the same. And you can phrase that in terms of a combinatorial or a topological object or argument if you want. And it works as follows. So you write down this object, this space, this topological space. It's a certain type of graph in this case, K4. And well, its vertices, if you want, are all of those expressions. So this is sometimes a vertex, this is a vertex, this is a vertex, here's one, and here's one. And you connect them by an edge, which are my red edges here. So 1, 2, 3, 4, 5, if they are related by one of those small and easy moves. So whenever you have one of those small moves connecting those two, you would draw an edge between them. For example, here, at this little piece here, I used the rule, the associativity rule, the small one, so I draw an edge between those two vertices. And that's my graph Kn. And the proof that A implies B is equivalent to proving that this graph Kn is connected, which is kind of a very nice and geometric, if you want, way of thinking about associativity. So A implies B, even only if this funny graph here is connected. And that's then in the end not so hard to show. And it's so well known, actually, as I said, that in almost all textbooks, you will find this one here, A, being the definition of associativity, although that's, philosophically speaking, as I said, kind of a wrong type of definition. But in some sense, it doesn't matter because you can show that it's actually equivalent to the correct form of a definition. And that's kind of what a coherent theorem is all about. A coherent theorem is the theorem of the form a finite collection of conditions. So in my example, it was just one, implies kind of all types of conditions you can imagine. And well, the main example is, for example, associativity. What I had before is just this little thing here implies all bracketings, right? So everything just, so A is if and only if B. And as you can see, actually, see it's the same. So this direction is really easy. So that's no problem. The other directions, of course, this is the main meat. The other direction, right? A finite number should imply all. Certainly, a finite number is contained in all. So the one direction is always easy. And there are many different geometric ways of thinking about associativity. So I drew those little graphs here because they're a little bit easier for me to draw. But actually, you can also think about a pair of pens. So something like a pair of pens. And that's the same operation. It's kind of a merge operation of whatever G and F. And you merge it to FG. And associativity is this really beautiful move here, which is kind of visually obvious on those surfaces, where you just pull down this leg here of your pens with three legs. So this is a pair of pens. It's called the pair of pens, and if you stack two of them together, you get a pair with pens with three legs. So I can pull this down and pull this up at the same time, and you end up here, and you can do the kind of the inverse operation. And that's kind of the associativity in terms of these funny cobalisms. And again, it kind of makes more sense than compared to this funny box picture. So it's kind of the abstract form of associativity has a geometric interpretation, while specific forms of associativity might be a little bit strange if you look at them geometrically. And again, the statement here is that this implies kind of the general Pence move. I'm not going to write down a general Pence move. I hope you can imagine what this is supposed to be. But this is just one example of a coherent theorem. Here's another one, which you probably have never thought about before. At least I have never thought about it before I learned this point of view on coherent theorems. Like, you can cancel multiplication by 1. 1 times f is f is equals f times 1, right? Times 1 cancels. So that's a unit element, whatever you want to call it, and you can get rid of it. And this is the easy condition, the small condition, and this should imply that everything, no matter how many ones you put wherever, they should cancel out. And again, this is a type of a coherent theorem, which has a really beautiful topological interpretation in this sense. So I think of 1 as being kind of a little cup, and times 1 would be then just taking the pair of pens. And as you can see here in the picture, you can just contract the cup into the pair of pens, and you just get a cylinder, which is kind of the constellation operation, right? So the cylinder is just taking f to f. Of course, it's just kind of the identity operation here. So this is another example of a coherent theorem. And there are a lot of basic coherent theorems, which you probably never really thought about why they should be of any importance, because it's usually relatively easy to see that they hold. So in this case, it's again not very hard to see. You don't need the geometric interpretation. But I say it again, it's kind of philosophically wrong to just impose the small condition. What you really should do is to impose the general condition, because that's what you want in practice, and then show that the small one implies the general one, because then again, in practice, you want to show that something is associative, and you of course only want to check one condition and not infinitely many. That's just more practical, and really more practical. Okay, but kind of the most famed one, which I'm only going to sketch very briefly on the next slide, because it's quite of a mouthful to state it. It's kind of a two-dimensional version of multiplication, if you want. It's Maclame's famed coherent theorem for monoidal categories. If you don't know what a monoidal category is, not so important. I'm kind of going to sketch it a little bit on the next slide, not really, but it's kind of a two-dimensional version of the classical multiplication, if you want to think about it like this. And then it's not quite clear anymore why it should be associative in some sense, but Maclame's coherent theorem kind of implies the same. There's a very finite number of conditions which imply kind of a general statement. So let's have a look at Maclame's coherent theorem. Don't ignore the details on this slide. I'm going to explain kind of the general setup. So in contrast to the one-dimensional situation, if you want, this coherent theorem in this case actually has three minimal equations. So the A part is here. And there are certain type of equations which are called pentagon, the square, the triangle. The triangle is not on this slide, but the pentagon looks like this and the square looks like this. So as you can see, there are brackets involved and some funny symbols, and everything is more two-dimensional. Ignore that, but you basically have three types of operations here. You have a pentagon operation, you have a square operation, and you have a triangle operation. And as I said, I haven't illustrated the triangle operation. on the slide. There was just no space anymore. Already, the slide is already quite full anyway. And Magnet's coherent theorem is has basically the same proof as what I showed you before, with this funny space where you just glue together to this graph that I called Kn. You can associate to this problem a topological space if you want, which you call Kn. Kind of Kn corresponds again to the kind of the number of symbols. The n corresponds to the number of symbols, and you associate a certain topological object to it, which gets higher dimensional. So this is glued together from pentagons and squares. That's why I have them on the picture. So this one here is a square, this one here is a pentagon, and so on. So it's kind of an object that you glue together from those. It's not so important that you get the details, but it really is the same idea as this one, just higher dimensional. And you glue them together, and you need to check a very similar statement. So instead of checking that the graph is connected that you get, you need to check that pi1 of the space you get, as you know what pi1 is, vanishes. Everything is just a more fancy version of what you've seen so far, but it's kind of a really nice, again, in geometric proof of a coherent theorem. So this whole coherent theorem, which I'm not able to formulate in a very slick way because it's really, really advanced mathematics for monoidal categories, you can just forget it in some sense and replace it with a geometric argument, so there will be a sequence of geometric spaces and you need to check geometric properties of them. So you kind of replace this fancy version of associativity again with some geometric property, which I think is pretty cool. Okay, let me wrap up. So I talked a little bit about wrong and correct definitions. For example, let me just do an explicit example. If you open now a random beginner's textbooks on groups, whatever, you probably will find the definition of a group being, well, it has a certain operation, it has a unit, it has inverses, and have within associativity. And associativity is probably phrased in my A, so in this HGF equals HGF with two different brackets, which is kind of the wrong type of definition. Because what you really want is that all brackets are the same. And in order to go from one to the other, this is where a coherent theorem comes in. And very often, coherent theorems actually have a nice interpretation. So the easy one that I showed you in some sense was this graph that you wanted to show to be connected. So associativity is a general form, is equivalent to this graph being connected, which is kind of a funny statement. In any case, I hope you enjoyed the video, and I also hope to see you next time.